Welcome to the first presentation in the Focus Training Group Electromagnetism series. In this presentation, we will be looking at flux density. Electromagnetism is one of the four fundamental forces. The other three are weak nuclear force, strong nuclear force, and gravity. Electromagnetism was historically known as electrodynamics and was documented as far back as 1600 when mariners noticed that lightning caused a compass needle to move. Electromagnetism as we know it today became widely known when Hans Christian Ørsted observed in 1820 that a compass needle was deflected when a nearby battery was turned on and off. His findings were expanded and refined by Michael Faraday, James Clerk Maxwell, Oliver Heaviside, Heinrich Hertz, and others. Flux density can be thought of as the strength of the magnetic field. The symbol for flux density is beta, and the unit for flux density is Tesla. As we see from the formula, there are two factors which affect the flux density. The magnetic flux, which can be thought of as the strength of the magnet. Magnetic flux is given the symbol phi and is measured in Webers. The second is the area of the field, which is measured in square meters. To explain the formula, we see that the flux density is proportional to the magnetic flux. If we make the magnet stronger, the flux density will increase. We can also see that the flux density is inversely proportional to the area. If we spread the field over a larger area, the flux density will decrease. Next, we will look at some calculations using this formula. In this first calculation, we are asked to find the flux density of a field with a magnetic flux of 6 Webers and an area of 0.02 meters squared. As we can see, this is quite a simple sum. We just divide the 6 by the 0.02, which gives us an answer of 300 Tesla. For our next calculation, we are asked to find the flux density of a magnetic field when the magnetic flux is 60 milliwebers and the area 30 centimeters squared. So the first thing we do is we convert milli to whole Webers. As we know, milli means 1,000th, so we could divide 60 by 1,000, or we could multiply 60 by 10 to the power of minus 3, moving the decimal point 3 spaces to the left. So 60 milliwebers becomes 0.06 Webers. The next thing we need to convert is centimeters squared to meters squared. And if we think about how many 1 centimeter square blocks we would need to fill a square meter, we would need 100 times 100, so we would need 10,000 centimeter squares to fill a 1 meter square. So to change 30 centimeters squared into meters squared, we can either divide 30 by 10,000, or we can multiply 30 by 10 to the minus 4, skipping the decimal point 4 places to the left. So our 30 centimeters squared becomes 0.003 meters squared. Once we have these two whole numbers, we can pop them into the formula and we get 20 Tesla. We could use indices and cancel out the indices, but it's easier to see the steps if we change to whole numbers. For our final calculation, we can see that we've got a magnetic flux of 80 millivebers and an area of 200 millimeters squared. So we know to change millivebers to vebers, so our 80 millivebers would become 0.08 vebers, but we need to think about millimeters squared. And again, if we think about how many 1 millimeter blocks we would need to fill a square meter, we would need 1,000 times 1,000, so we would need 1 million square millimeters in a square meter. So to change our 200 millimeters squared into meters squared, we could divide 200 by a million, or we could multiply 200 by 10 to the power of minus 6, skipping the decimal point 6 places to the left. So our 200 millimeters squared becomes 0.0002 meters squared. Once we have these whole numbers, we can pop them into the formula and we end up with 400 Teslas. We hope this has been helpful, and in our next presentation we will look at transposition of formula.